Okay, welcome to part 2 of the Introduction to AS Chemistry tutorials. This one is going to be about equations, writing equations and balancing equations. Again, a really key skill. And to be able to write equations and balance equations, what you need to be able to do is come up with the formula of compounds. So if you haven't watched the formula of compounds one and just seen what the formula of some of the common simple compounds we're going to be dealing with are, then it's a good idea to look at that one first, because otherwise it's a little bit tricky if you don't know the formula. Okay, so let's go to this screen. So chemical equations. Now by chemical equations, I'm not talking about word equations. If you've written word equations in the past, you can more or less forget they ever existed, because when we talk about writing a chemical equation at A-level chemistry, we're talking about simple equations. There are no other chemical equations which are really terribly meaningful. Word equations don't help us a lot. You can't do much with them, so we won't be looking at those at all. So what I'm going to do is just illustrate a few simple principles by a couple of really simple equations. Then we'll just look at how to balance a few more perhaps challenging ones, but nothing really complicated. You don't get massively complicated equations to balance at A-level. So let's just take a simple combustion reaction. Okay, hydrogen reacting with oxygen. The first thing to point out is that if I say I'm going to write an equation for hydrogen reacting with oxygen, hydrogen gas goes around as H2, oxygen gas goes around as O2. It's not individual atoms. We could write equations for things that happen with individual atoms, and at times we will do that. But if we're just writing this simple equation for hydrogen reacting with oxygen, we're talking about H2 and O2. If you had an equation involving nitrogen, it would be N2, or a halogen like chlorine, it would be Cl2. A lot of simple gases go round as two atoms joined together, diatomic molecules as we would call them, two atoms in a molecule. Okay, a little arrow there. So these things here that we're joining together we'll refer to as reactants. So they're the things we mix together and hope something's going to happen. Okay, sometimes above and below the arrow we'll put some reaction conditions or additional reagents or catalysts or things like that. In this case I'm not going to do anything. In the product here is H2O, which is water. Okay, now the issue here is that to make this equation balance, we've got two hydrogens here. We've only got one oxygen there, but we've got two here because oxygen goes around as two atoms joined together. And we can't make less atoms than we started with, or we can't make more atoms than we started with. So the number of each type of atom on each side of the equation has to be the same. We're okay with the hydrogens, we've got two on both sides, there's not a problem there. On the other hand, the oxygen, we do have an issue there. Now the simplest way to balance this is by saying, well, we don't need all of these oxygens. Why not just have there. Now that equation balances, because a half of 2 is 1. Now the thing to get your head around here is we're not saying put an oxygen molecule in here. We'll be reacting real quantities of these materials. So by saying half an oxygen, we're just saying we're going to have half the number of oxygen molecules knocking around as we've got hydrogen molecules. So to make water we need to mix hydrogen and oxygen in a 2-to-1 ratio. Now the alternative way of balancing this equation, if I get a different colour, let's go for red, would be to put a 2 in front of there and a 2 in front of there, and you'd only have 1 there. When you've got a 1, you don't put in the 1, you just leave it blank. Okay, now that would be another way, and there's nothing wrong with doing it that way. However, when you come to do things like enthalpy calculations in developing fuels, which is one of the first units that you use, you are often working out an energy change for a specific amount of substance. So it's often important just to have one here, not two. Otherwise you'll get your calculations wrong. So the use of fractions in balancing equations is really quite important and fundamental. Okay, so that's a nice simple example to get us going. Let's go back to black. So if these are the reactants, this is a product. So we put the products, in this case there's only one product, over here. Okay, let's take another one. A reaction that you do all the time in the lab. Let's take some methane, which is CH4, which is one of the common compounds I mentioned in the first video. React it with some oxygen. Excuse me. And when methane burns, and hydrocarbons burn, it burns completely, you'll get carbon dioxide being formed, CO2, and H2O. Okay. Now this is a little bit more complicated because you've got oxygen here, and you've got oxygen there, and you've got oxygen there. So you've got three oxygens. Okay. When you've got that sort of situation, what you want to do is start balancing the equation based on an element that only appears once on each side of the equation. So, for example, carbon appears here once and appears here once. We've got one carbon there and one carbon here, so there is no need to balance the carbons. So one methane molecule will make one carbon dioxide molecule. That's it. The other element that we've got once both sides of the equation are the hydrogens. So we've got hydrogen here and we've got hydrogen over here. However, we've got four hydrogens here and only two in a water molecule. So to get the four hydrogens, okay, we've got to make two water molecules. So we're going to have a 2 in front of the H2O there. Okay, so when you burn one methane molecule, you're going to generate two molecules of water, because each methane molecule has four hydrogen atoms as part of it, which go to form two water molecules. Now the hydrogens and the carbons are balanced, so we can't change what's in front of here, and we can't change what's in front of here or in here. So let's look at how many oxygens we've got. We've got two O's there, we've got 2 times 1, we've got 2 O's over there. Okay, so two water molecules has 2 oxygens total. So that's 4 oxygens there. We've only got 2 here, so to get the 4 oxygens we need, we put a 2 in front of there, and that will be a balanced equation. Now, there's an additional facet of equations which you'll meet, and that's something called state symbols. So state symbols represent the physical state, and you'll have met these before: G, L, S, and AQ. There are others, but these are the ones that we'll meet. So gas, liquid, solid, or AQ means aqueous, dissolved in water, something that's in solution. So for example, this is, unless you get very, very cold, a gas. Likewise, a gas. It's an interesting one here, because if we did this reaction at standard conditions, water would be a liquid at room temperature. If we did this reaction sort of in the conditions that it actually happens, the water would be produced as water vapor, as a gas. It would later then condense perhaps to a liquid, but so we're going to produce it as a gas here. Likewise, here methane is a gas, gas, gas. Let's say this one is being done at standard conditions, which would be 298 Kelvin or 25 degrees centigrade, in which case that one would be an L, liquid. Okay. Let's just do one other combustion one. Let's pick something a little bit more complicated. C4H10 is butane gas used in camping gas stoves, and again it makes carbon dioxide and water if it burns completely. So this time, if you look at the carbons, we've got 4 here and only 1 there. So we're going to make 4 carbon dioxide molecules. One butane molecule can make 4 carbon dioxide molecules. Well, it's got 10 hydrogens here. We've only got 2 here. So to make the required number of hydrogens over here, we're going to need 5 water molecules, because 5 times 2 is 10. So if we look at how many oxygens we've got, 4 times 2 gives us 8 over there. 5 times 1 is 5 over there, 5 O's, which gives us a total, if I'm not mistaken, of 13 oxygens. Okay, so if you divide 13 by 2, because you've got a 2 here, that gives you 6.5 O2s. And this is an example of where you need to use a fraction for the to make it balance. Now, of course, you could double this all up to get rid of the fraction, but that's actually quite a bad thing to do, because you'll be doing calculations based on what happens to 1 butane, not 2. So doing it this way is better. Okay, so that's some simple balancing. Let's look at another one. So these involve covalent molecules. Let's look at some solutions. This is a very simple reaction between sodium hydroxide and hydrochloric acid to make sodium chloride salt, and just move this across to the right a little bit, and a bit of water. Okay, now this reaction is sodium hydroxide solution reacting with hydrochloric acid, HCl, to make sodium chloride, NaCl, table salt, and water. Now, you might notice that this reaction actually balances straight up, because we've got 2 hydrogens here, we've got 1 there, we've got 1 there, and we've got an oxygen there, an oxygen there, sodium here, and a chlorine there, chlorine there. So balancing, it's happy days. Okay, but this illustrates something different on the state symbols. That's aqueous. That's aqueous. Sodium chloride soluble in water, so that will be formed as aqueous, and that's a liquid. This is an alkali reacting with an acid. We can deconstruct this a little bit to make what we call an ionic equation, so we can ignore the sodium ions, the chloride ions, and the chloride ions and the sodium ions here, because they're actually just floating around in solution, not really doing anything much. The sodium ions and the chloride ions aren't really involved in this reaction at all, because in solution sodium hydroxide knocks around as a sodium ion and a hydroxide ion, which are quite separate. Likewise, the HCl goes around as separate ions. We say it's been dissociated when it goes into water. So what's actually happening here is OH minus, a hydroxide ion, is reacting with a hydrogen ion to make a molecule of water, which is what you'll find happens whenever you react an acid with a base or an alkali. An alkali is just a base that's been dissolved in water. Okay, an alkali is just, if you take something called a base is something that can accept a proton, put it into water and it dissolves, you make an alkaline solution. Okay, so that's that one. Let's pick a different one. Let's pick this one. This is an oxide anion. I didn't put it on the other list. This is a carbonate ion, CO3 2 minus. I need 2 sodiums. Sodium carbonate will react with, let's have sulfuric acid, and it will make, so when you've got a carbonate reacting with an acid, it gives you a salt. In this case it's going to be sodium sulfate, and sodium sulfate is going to be Na2SO4, because a sulfate ion is 2 minus, gives you carbon dioxide, and it also produces some water. Okay, so if we look at this reaction, this one with our state symbols. That's in solution. Sulfuric acid is a solution. Sodium sulfate is soluble. Group 1 compounds are pretty much all soluble. And that's a liquid over there. And I think if you look at that one carefully, you'll find that that one actually balances straight off. If we take one other example, let's take potassium chloride reacting with AgNO3. Potassium chloride reacts with silver nitrate to produce silver chloride and potassium nitrate, which you're using gunpowder, but this is how you make it. That's aqueous, that's aqueous. This is a precipitation reaction because it produces silver chloride, which is a solid. And what's actually happening here, the potassium ion isn't doing anything, the nitrate ion isn't doing anything. What is doing something is the silver ion, which starts off being aqueous, is reacting with the chloride ion, which is also aqueous, to produce an insoluble ionic compound called silver chloride, which is used in photography. Okay. So just some examples of equations and a little bit about the principle of how to balance equations. So, and the use of state symbols. So again, a few key tools that you need to know about.